When you use shopping sites like Snapdeal, the products you are looking for will be listed out in seconds on the screen. Suppose the programmer who manages the website has created a database of all the products under one set, then do you think the website based on that database will be able to display the list of products in just seconds? That's impossible. Well then, how does the product you are looking for gets listed like that? In order for the website to run faster, the programmer would have divided the database into many sets. Suppose you're looking for a big car, say Tata SUV in eBay, then the database would list out the common items in two sets, that is, brand name Tata and car type SUV. This is where the concept of intersection in set theory is useful. In this video, we shall check out the concepts intersection, union, and difference in set theory. Before we jump into the topic, let us recall few terms we shall be using today. A collection of distinct objects is a set, and every object inside the set will be called an element or member of that set. A set can be represented as set builder form, roster form, and as a Venn diagram. If all elements of set A is in set B, we call A to be a subset of B. If at least one element of A is not in B, then A is a proper subset of B. The set containing all elements of the problem under consideration is called the universal set. And then the set that contains every element of U that is not in A is called complement of set A. In a Venn diagram, universal set is represented using a square and every other set is represented commonly as a circle. When a universal set and two other sets, say A and B, are considered, then four regions will be formed in that Venn diagram. This region colored yellow will contain elements of A which is not in B. This region in blue contains elements of B which are not in A. This region colored green contains elements which are present in both A and B. And finally, this region in pink contains all elements of U which are not in A and B. Likewise, in a three-set Venn diagram, this region in green contains elements in A and not in B and C. This region, colored blue, contains elements of B which are not in A and C. This region in orange contains elements of C which are not in A and B. This region in pink contains elements which are common in sets A and B, that is A intersection B. This region in red contains elements B intersection C, and this region in lavender contains elements of C intersection A. This region in the center, which is cream colored, contains all elements common between A, B and C, that is A intersection B intersection C. This region, colored light pink, contains all elements of U which are not in A and B and C. To know more about the terms I recall now, the link to the respective videos are given in the description box. Do check it out. Just like when we add or multiply two real numbers, we get a new number. When we use an operator on two sets, we get a new set. P intersection Q is the set created using all elements common in both sets P and Q. It will be represented in set builder form as the set of all x such that x belongs to P and x belongs to Q. In a Venn diagram, this represents the region that overlaps set P and set Q. In this diagram, you can see that P intersection Q is a subset of both P and Q. Suppose that P is a subset of Q, then can you guess what P intersection Q will be? Yes, the common region of P and Q, that is, set P, will be P intersection Q. Now what if P and Q were disjoint sets? Then how would P intersection Q look like? As there is no element common between P and Q, P intersection Q will be nothing but an empty set. Also, when a set intersects with an empty set, the answer will be the empty set. Also, when a set intersects with the universal set, the answer will be that set itself. The operation we will be using now is union. Let P and Q now be two non-disjoint sets. Then union of set P and set Q will be the set of all elements of P and Q. It will be represented in set builder form as set of all x such that x belongs to P or x belongs to Q. In a Venn diagram, it will be the region made of both P and Q. If set P was a subset of set Q, you might see that union of P and Q is set Q itself. Now, if P and Q were disjoint sets, then P union Q will be both the regions P and Q. The next operator we are going to use is difference. Now, set A minus B will be the set of all remaining elements of A when elements of set B are removed from set A. In set builder form, it will be represented as set of all x such that x belongs to A and x does not belong to B. In a Venn diagram, it will be represented like this. This shaded region will be A minus B. Few things to note here is that number 1, A minus B is equal to A intersection B complement. Number 2, if A minus B is equal to B minus A, then A will be equal to B. And number 3, if A minus B is equal to A and if B minus A is equal to B, then A intersection B will be an empty set. The next operator in the picture is symmetric difference. Now, symmetric difference will be the union of A minus B and B minus A. In set builder form, it will be represented as A delta B, which is equal to set of all x such that x belongs to A minus B or x belongs to B minus A. In a Venn diagram, A delta B will be this region. Few points to note here is that number 1, symmetric difference between A and A will be an empty set. Number 2, A delta B will be equal to B delta A. And number 3, A delta B will be equal to A union B minus A intersection B. This you can clearly understand from the Venn diagram. For better understanding, consider this example of set A and set B. We are going to find A intersection B, A union B, B minus A, and A delta B. Now let's find A intersection B. Since A intersection B contains only common elements of sets A and B, let us compare each element of A with set B. Element 2 of A is not in B, element 3 is common, element 4 is not in B, and element 7 is common. Therefore, A intersection B will be equal to set of elements 3 and 7. Now let us find A union B. A union B will be all elements of A and B. So first, let's write all elements of A and write elements of B which are not in A. So, A union B will be set of all elements 2, 3, 4, 7, 1, 8 and 10. It really doesn't matter in which order we write these elements. Now, A minus B will be elements of A minus the elements of B. That is, it will be the set of elements 2 and 4. Finally, symmetric difference will be union of A minus B and B minus A, remember? So that will be the set of elements 2, 4, 1, 8 and 10. We do know how to shade A union B and A intersection B. Let us now see how to draw Venn diagram for sets under operators. Number 1. A complement union B. First shade A complement, next shade B. These two steps together is A complement union B. Number 2. A union B complement. This will be shaded the same way as problem number 1. Number 3. A complement intersection B will be like this. First shade A complement, then shade B. Since the operator is intersection, the region common between these two steps will be A complement intersection B. Number 4. A intersection B complement. This will be shaded the same way as problem number 3. In the same way, we can find A complement union B complement and A complement intersection B complement. One thing to note is that A union B the whole complement will be equal to A complement intersection B complement. And A intersection B the whole complement will be equal to A complement union B complement. These are called identities because these are true for any two sets. Why don't you check for yourselves by drawing Venn diagram? Likewise, we can draw Venn diagram for 3 sets. That is, we can find A intersection B intersection C and A union B union C. Why don't you pause the video wherever needed and verify the diagram for yourselves? First, A intersection B complement intersection C complement. Second, A union B intersection C. Since values inside braces are given priority, first shade B intersection C and then combine it with A. Next, A union B union C complement. Next, A union B union C the whole complement. Finally, A intersection B union C the whole complement. Just like how for real numbers, we have laws like commutative, identity, associativity, and distributive, same way for sets also we have laws like commutative, idempotent, associativity, distributive, De Morgan's law for set difference, and De Morgan's law of complementation. The difference is that in real numbers we have addition and here in sets we have union, and instead of multiplication we have intersection here. That's all. These laws can be verified by drawing Venn diagram for LHS and RHS, and we will see that they both are equal. So, in this video, we checked out operators on sets like union, intersection, and difference. More examples on these concepts will be covered in another video. So, if you have found this video to be useful, do share it with your friends and family. Hit the thumbs up button if you have liked this video and share your views and thoughts and queries in the comment section. Check out the description box for links of all the concepts to recall, and don't forget to subscribe to Fun Maths Academy to be updated on videos time to time. Thank you.